Hi, Professor Cook. Good morning.
Yeah, good morning.
Good morning, Professor Han. Can you hear me? Hi, Professor Han. Are you there?
Hello.
Hello. So I can hear you. Good morning.
Good morning.
Okay. Okay, Professor. So shall I begin for today's presentation?
Sure, go ahead, please. Thank you.
Okay. Very well. Okay. So
wait a minute. Let's wait a couple more minutes.
no problem.
Okay.
No problem.
Kubana Gyosu is not here yet.
Okay.
Just a couple more minutes. Thank you.
I see.
I think you can begin now.
Okay. Okay, very cool. So today's my presentation. Yeah, it is a paper which is published in CVPR 2021. So it is called Ensembling with Deep Generative Views. So for today's presentations, so I would like to separate it into several parts. So the first, we'll introduce some backgrounds about the gun inversions and also the data augmentations with generative models. And then we will go to the proposed method and his experiments. And I will give you a brief conclusion. And finally, I will briefly introduce a little bit about my personal studies of gun inversion. Okay, let's start. So about the background. At the very beginning, for starters, so I would like to introduce some basic knowledge about the gun inversion task. Actually, you know about the traditional gun. The traditional gun, it is usually do the mapping work from a lantern vector Z, from the lantern vector Z, which it is obey the Gaussian distribution, and then we sample a lantern vector Z from this distribution, and then we use the generators to map this lantern vector to an image. So we can generate the fake image of the face. So the basic process, it is to map from this lantern space to an image. So if we want to edit a real image, how we can do that? So suppose we have a real image of President Bush. So the first things we want to do is to invert this real image into the lantern space. Suppose we have an encoder. We have an encoder to do the inversion things. So we invert this real image into the lantern space, which it is represented by the Z star. Z star here. The Z star here means the lantern vector of this real image. So next, we can do a couple of things. First, we can just do the reconstructions. So we use the generator to reconstruct from this Z star lantern vector to rebuild this real image so that we can see they are very similar, just tiny differences. Okay. And then if we want to do the edit on this real image, how can we do that? So the first things, so we can manipulate on the lantern space. So we can add up small tiny operations, which it is represented as the N1. So that we add it to the Z star lantern vector, and then we use the generators to generate this image so that we can get this decreased age images of President Bush, right? So if we want to add a smile to him, so we can do another tiny operation on the lantern space so that we can add a smiling President Bush. Okay, so this is some overview, some basic knowledge about the gun inversion task. So next, there are several kind of the methods to finish this kind of the task. So for the sub picture A, so that it represents a process about the traditional gun. The traditional gun, it is basically we sample a lantern vector Z from a distribution, and then we map it with to an image with a generator. So this is the traditional gun. What does the traditional gun do? So in the second sub pictures, we show in B, C, D sub pictures. So I show some kind of the gun inversion methods, which it is called the optimization based inversion and learning based inversion, and also the hybrid approach. So for the B, so suppose we have the lantern vector here. We use a generator to reconstruct our image. So that we have a reconstruct image X, and we have another kind of the real image. So we compare the loss between them, and then we optimize directly to the lantern vector Z. So this is the optimization based inversion. So second one, it is the learning based inversion. So suppose we have we bring an encoder here, so that we can encode this real image into the lantern vector, and then we use the generator to reconstruct it, and then we compute the loss between the reconstruction images and the real images, so that we can use this loss to optimize the encoders. So that this is the learning based inversion. So we can also combine them together, combine the optimization based inversion and the learning based inversion together. So we can get a third one. So it is called the hybrid approach. So this is the mainstream of the gun inversion methods. So okay, we finished to talk about the gun inversion. And then let's move to the data augmentation with the generative models. So it is a really big contents. So it can be used, the data augmentation with the generative models can be used in many kind of the areas, such as the
Can you go back to the previous slide?
Of course.
On this, this optimization only works per each image, right? If you're talking about some optimization method to go back to Z.
Yes.
You have to do the optimization for each individual image.
For each image, right? For each input.
Something like a gradient-based, maybe optimization. I assume that's what you're talking about here.
Yes.
Okay. All right. Thank you.
Okay. Let's go back to the data augmentation with the generative models. So it can be used widely. So I will not dig into it. So I just want to do the conclusion of this kind of the methods. So using the GAMs for the data augmentation, it is still limited by the domain gap between the generative samples and the dataset images. So how we can do that? So it is still an open questions to the researchers. So in order to tackle this kind of the problems, so the authors of today's papers have bring a kind of the algorithm. It is called the ensembling with the deep generative views. So let's move to the proposed method. Okay. Overview. Okay. Overview of proposed methods. So basically, by and large, so this kind of the assembling with the deep generative views, these papers, these models, it is a data augmentation methods for a downstream task called image classification task. Okay, you just need to remember it is only a data augmentation methods for the image classification task. Okay, let's move to this picture. So in this figure, we have the input here. We have a very cute cat here. So we call it input image. So suppose we have this kind of the one input images, and then we want to inverse it into the lantern space here, with any such kind of the encoders to reverse it into the lantern space. And then we use a generator to synthesize a series of the generator samples. We showed it here. So we have 3 generator samples here, 3 cats here. They are the fake images. So when we get this kind of the, oh, sorry, I forget to introduce. We need to do some manipulations on the lantern space. After we do the manipulations, so that we can use the generators to generate different kind of the cats based on the real images. So that after we get the generated samples, so we pass it to the classifier, so that we can get our predictions for each image. So we have 4 predictions. The predictions for the real images and 3 predictions for the fake images. And then we just consider them together and then to get our final predictions. So this is the basic knowledge, some basic ideas, key ideas of this proposed method. It's a data augmentation method for the image classification task. So how can we do that? We'll go to the details. Okay. So before we go to this proposed methods, I want to make sure that you know something about the GAN, the basic knowledge, the fundamental knowledge about the GAN, especially the style GAN 2, So I will go I will go through it very quickly. So we have the style gun tool here. So it includes two networks. The first network, it is the mapping networks M, okay, function M, and then the generator G here, it is the function G, and then we have three inputs. First input, it is the lantern vector Z in the lantern space Z, and then the lantern vector W, and then we have the noise inputs. Okay, so if we want to synthesize an image, and then we need to start from the lantern vector Z. We pass it through the mapping network F, and then we can get the lantern vector W, and then we use this W as a style vector, and then we can send it into the generators to generate our desired image X here. So that according to the style gun 2 paper, so it finds that it is more effective to manipulate an image in the lantern space W. Yeah, it is more effective. So in this paper, so we focus on the lantern base W. So in order to edit an input image X, so we first need to map it into the lantern space X, and we need to use the following loss functions to optimize the networks, including network, the generator and the mapping networks. We will go back to this loss function later. Okay, this is in this slide. I only want to tell you about some basic knowledge about the style gun tool, so you can be prepared for the next step. Okay. Okay. So let's go to the proposed method. Okay. At the very beginning of the proposed methods, so we always start from a pre-processing of the image. We want to make sure that our input image, the input image can be centered in this image. So let's make an example here. So we can see in this in this picture, we want to make sure that the woman's face can be in the middle of the images, and this car, and also this face of the cat. So we want to make sure that the main object, it is located in the middle of the images, so that this is the first things we need to do to pre-process our images to make sure that the object, it is located in the right place. Okay. Second, we move to the encoder initializations. Okay, we use this. So we use the images to pre-train the encoders to make sure that these encoders, it is ready for the image mapping and the next classification task. So we use the loss function here. It includes the image loss functions, perception loss, and the lantern loss here. So the final output of this process, it is optimized encoders, or we can say it is a little bit confused. We can call it encoder, and we can call the mapping network F here. So the encoder, it is be equal to the mapping network F here. So that this is the second step. We want to get a pre-trained encoder, the pre-trained mapping.
Hold
network.
on a second.
Of course.
For the loss function expression, on that line here, L sub image of X comma G sub E sub X.
Yes.
I assume that's the reconstruction loss, right?
Reconstruction loss, definitely right.
But then the second term,
yes,
L sub latent, and then W. Okay.
Okay. The loss term here, called the loss latent, the latent cost. We want to do basically it is a L2 loss. It compares the distance between the W and the it compares the loss between the W. I think that's a little bit I do something wrong here. Sorry. So basically here it is only the ZX, no G here, no G here. There is some mistakes here. So basically this loss, it is to compare the distance between the W and the output of the mapping network here. So the W, it is some kind of the label, or we can say that it is have been provided. It is have been provided something like the pre-train latent vector W, something like that for each class. Suppose we have we are working on the CIFAR 10 dataset. We have something like the class of the cat and the dog. So that this vector W, it is corresponding to one class, the latent vector of one class images. It is already been provided.
Before you go on and really explain a little more, I'm still trying to figure out, okay, your input latent vector is Z. You start from there, right?
Yes, you're right.
And your G sub, but then you also have an X here. Where, how does X factor into this thing here? Right now, you're only showing the generator side, right?
Yes.
Style again to generator. So there must be another encoder network somewhere that brings X back into the latent space. So what is that function? Is that function E here? E sub X? Is that what it is?
Yes. So we have a encoder here. The encoder here, it is corresponding to the E function. We can use the encoders to map our input image to the latent space W.
Okay, all right. So, okay, I got it. And so you're matching basically a encoder loss or the latent matching loss is one, and reconstruction loss is another here.
Yes.
And your equation has an error that G shouldn't be there, like you said.
Yes.
Okay.
I make a mistake.
And then the second line here is argument of okay, this is the whole thing here. Okay. So that's the E star. So okay, so that's the training. Okay. You're training the encoder here.
Encoder.
Okay. All right, got it.
Okay. And then if we get an input, this is the third step. In the third step, we have an input image, or certain input images here. X. We want to use this input image to optimize the mapping network F here, so that in this step we want to get the optimized latent vector W. Also, we can call the latent vector W star here, so that we only use single image to run the alterations 35 to 40 steps. So it costs only half a minute to do the optimize on the certain image, images. So we can get the optimized latent vector Ws for these images. So, and then we can evaluate the quality of W by observing the gun reconstructions, which is represented here. So we have our input image here. It is a woman's face, and then we map it into the latent vector W, and then we reconstruct it. So we can see the reconstruct result here. They are very similar. It represents we have already get the optimized latent vector W. So we can evaluate the quality of W by observing the gun reconstruction results here. So this is the third step. So we have already done to the mapping from a real image to the lantern vector. This is the first step. And then for the second step, we want to do some manipulations on this kind of the lantern vector W. So in this paper, it offers 3 methods to do the manipulations. So the first one, it is to simply sample from isotropic Gaussian ball centered at the optimized latent. So we can get a disrupted latent vector W here, which it is represent as a W hat here. So this is the first method to do the get the perturbed latent vector W. So second method, it is called the principal directions. We use the PCA. We use the PCA to get the principal directions of the principal direction and the eigenvalues of the latent vector W's, so that we can use this kind of the PCA results to do some manipulations on the latent vector W, so that we can get our outputs here. So this is the second method. And for the third one, so that
wait, hang
okay,
on a
of
sec.
course.
You go back on this PCA thing.
Okay.
When you initially talked about the previous method where you look for W sub tilde, this optimized latent vector, right?
Yes.
You only get 1 per each image.
Yes, of course.
And here, how are you getting these distributions? In order to get a PCA, you must have some distributions here, right? How do you get more than 1 vector?
Get it from 1 vector?
How do you get more than 1 vector here? Because when you do the iterative optimization, you only can compute 1 vector, right? Per each image. So how do you get the distribution of latent vectors?
Latent vector. Oh, this is a problem I never consider. Oh, so I suppose it has been done. The PCA operations, it has been done under a bench of the image. I say on the bench of the image.
Yeah, but then but if the images are different, your vectors for each image is going to come out very different, right?
You're right.
I mean, what you want here, it seems to me, is that you want the same image or the similar images of different maybe features, maybe older, young, or whatever these manipulations you want to do later.
Okay.
That you want to identify by using these eigenvector methods, right? So maybe that's what you have then. Is that what they do? More than 1 images? You get the distributions of these variations?
Actually, in this part, I'm not so clear about how you can do the PCA operation here. So that I will look to the code later. So the
okay, all right,
okay,
all right,
okay. Let's go back to the third method, style mixing. So the lantern vector X here, it is a matrix B by D dimensions. So the Style Gun 2 papers, it offers some ideas about the representations of this kind of the in the first dimension of latent vector W. So we can see here. In the latent vector W. So the first dimension, the size of the first dimension is B. So we call it the first four style codes. The first four style codes, it is called the cos styles, which it is represent the fundamental characteristics of this kind of the images. For instance, so some kind of the angles of these pictures, and also the locations of this face, and the shape of this face, and the shape of these cards. So that it is called the cos styles. And also we have the middle styles. It has been represented in the next 6 style codes. And then we have the fine styles. The fine style here, it means a very slight change from the images. For example, the color of the eyes, the color of the hair. So the texture of the skin. So it is very tiny change. So we call it the fine styles. So in this kind of the methods, we just want to manipulate.
Hang on a second here.
Of
Again,
course.
I'm kind of lost here because you have W star, basically a matrix here, right?
Yes.
And early layers for coarse patterns and later layers are for fine details. How can you be sure? First of all, this W star, I assume, is a latent vector, right?
Yes, you are right.
But then now it's saying that it's a matrix, so I'm not so sure what that means. So again, I'm wondering, whether you have multiples of these images forming latent vectors that you can combine it into matrix, perhaps. But I'm not so sure. You haven't explained how you got this matrix to begin with, and then how you can say these layers have these coarse defined kind of a layering. And how do you ensure? How do you know that that's how it goes?
Okay. So basically, you need to know about something of the Style Gun 2. Style Gun 2, it is to use this kind of the latent vector W to control the style of the synthetic images. So how can it do that? So suppose we have the latent vector here, latent vector W here. It is a matrix. It is a matrix B by D, and then in each we send it into the generator layer by layer. So the cos style here, that means the first 4 layers. The first 4 layers of the Style Gun. The first 4 layers of the Style Gun 2 generators. So we serve first 4 dimension of the latent vector W into the generator, so that we can control the cos style of these synthetic images. So
what you are saying is then in this figure, the W is fed into, different parts of W is fed into each of these generator layers. Is that what you're saying?
Yes.
So they are not, not the same W's go into each of these boxes.
Of course, you are right.
That's how it was. I thought that they were the same, at least the way it was explained earlier, but now here, that's not how they're doing it?
It is not the same. So suppose we have the in these generators, in this generator, suppose we have the 36 layers. So the first 4 layers control the cos styles of the image, and the second 6 layers control the middle styles of this image, and the final and the rest of the layers control about the 5 styles of this image. It is already
okay. So I see maybe that I didn't really understand how W or yet. So Z must be the vector, but then W is a matrix then, the way that you compute this?
Yes, it is a matrix.
Okay, all right. And the way that the generator or the GAN structure is that it goes through the upsampling basically. That's what it has to do. And so typically you feed in whatever Z or W, and that the same information goes all the way from the coarse to fine. But in here, then you're really feeding different parts of embedded W matrix into each of the upsampling scaling process here then.
Yes, this is style gun.
Okay, and this is the same, right, from the beginning, the same style GAN that.
Oh, I couldn't hear you.
Okay, you can go on. Thank you.
Okay, no problem. Okay, thank you for the questions. Okay, and we can use this kind of the style mixing methods to do the to do some manipulations on the latent vector W's, so that we can. So just to remember, we have the 3 kinds of the methods to do the perturbing on the latent vector W. So that, okay, finally we go to the our downstream task.
Can we go back to the picture again?
Okay, of course.
Yeah, so the star gun 2 generator that you have on the right side. So that picture is the very standard star gun 2 generator model, right?
Yes.
And so in that figure, you have W, right, on the left-hand side that sort of like feeds into the middle column boxes there, right?
Yes, of course.
But then you have like W2, W3, and W3 also, which I presume that they are sort of like a subset of the W matrix that feeds in. So so as far as the box is concerned, the gray box, each of the gray box in the middle, right? So you have sort of like the input that feeds into the gray box from 2 places, right? One on the left-hand side and one from the top to the bottom. Is that how it is, or is it just assuming that W2 and W3 are, or is it just trying to say that individually W2, W3, and so forth are coming from the original W matrix on the left-hand side?
So I would like to explain it. So in the generator, we have several inputs here. So the first input, it is from the W. The W lantern vector controls the style of this picture.
Oh, okay.
Okay. And the second input here, it is the noise. The noise can decide some details of this kind of the pictures from these pictures. And then we have the third input here. It is a continent, so it doesn't matter. It doesn't matter. So it doesn't matter. So basically we have 2 inputs. So the inputs to control the style, the basic structure of this picture. And then the second one, it is the noise. The noise provides the details of this image.
The details, okay. Noise provides the details. And then the style is done by
lantern vector X. Yes.
What about W? That goes into from the top to bottom. top down.
Top down. So
within each of the gray box, there's W. The W's.
Yeah, the W here. So W here control the style of these images.
I'm trying to figure out the way how the W is being fed in.
Okay.
So obviously you have two arrows, right? One going in from the left to the right, and one from top to bottom.
Top to bottom.
But top down.
Top down. So
top down W, and from left to the right. You have two W's. I
have two W here. Oh, I just think the W here maybe it is just the continent. I'm not so sure that the by and large I only focus on the.
Okay. All right. Okay. You just think that the input is just feeding in from left to the right from the W.
Yes, left to the right.
Okay.
You need to
right.
Focus on the main process, right? Okay. Okay, no problem. Let's move to the downstream task. So don't forget about our downstream task. We want to use this kind of the generated samples to optimize, to boost our classification task. So you know that for the classification task, it is quite simple. We have an input images and a train and a pre-train classifier. See here. So basically the classification task can be formulated as a. So we send the input image X into the classifier so that we can get a prediction here. So okay, this is our downstream task. And then how to utilize the generated samples. So we need to the process of the assembly. So we jitter the optimized latent vector X, latent vector W's to apply a series perturbed W1 hat from the Wn hat, so that we can use this kind of the perturbed latent codes to generate a series of the generated samples here. So that when we do the decision of each input images, we involve the decisions of the generator samples. So that here it is here. It is our final decisions. It is our final predictions of the real images. So that in here we consider about the decisions of the real images, and then we also need to consider about the decision of the generator samples, and then we combine it together with a hyperparameter alpha. So that this is how the decision comes. So that we can use this kind of the cross entropy loss to optimize our classifier so that we can get our final results. Okay, so the main task, it is the classification task. But in this case, when we optimize our classifier, we need to consider about the decision of the generator samples so that we can get optimized and boosted classification results. Here.
Okay, just one thing I'm wondering here. Okay, so you do the jittering, basically putting some random noise.
Yes.
On the latent space.
Of course. And
you are hoping that the generator and the latent space that you created is continuous here then, right?
Why you say that?
Because when you do a little bit of a adding noise,
yes.
And this is the problem that that the variational autoencoder VAE solves, right?
Yes, of course.
VAE forces to have the latent space that's continuous.
Yes.
So how do you make sure that that latent space is continuous in here?
the continuous here, it is already been proved mathematically in the style gun 2 papers. Yeah.
How do they do it? That they have to train this to make sure that the latent space stays continuous, right?
Yes.
So how do they do something the same thing as what the variational autoencoder does?
I didn't go so into it, so that so maybe later.
Okay, because this is very important concept.
Very important, right? Oh,
because latent space has to be continuous. Otherwise, if you jitter it,
yes,
generated image is going to be complete.
Oh, sorry, I couldn't hear you. It's the network
Continuity
problem?
of the. Can you hear me?
Yes, sure. I can hear you now.
If the continuity of the latent space is not guaranteed, when you add a random noise, and hoping that the cat would be generated, you may end up having, I don't know, a grasshopper or something completely different. Right?
You are right.
That's the danger of these.
I agree.
Generators and the associated latent space.
Yes.
So you have to make sure that that is so, and that's a very important aspect.
Okay. Thank you for your advice. Yeah, I will consider it later. Okay. So that's how we can utilize our generated samples to optimize the classification task. So, okay, let's move to the experiments. So the experiments, it is basically the authors of these papers basically did the experiments on 3 data sets. The first one, it is the facial attribute distribution. So it is the data set here, it is the syllable A HQ, and then it contains 30,000 human face and with 40 labeled binary attributes. So in these evaluations, so we only focus on the binary classification task for each attribute. Okay, first of all, so we want to know about in this totally three gun perturbations. So which one it is the most effective? So we have the 3 here, the Gaussian one, and then the second, the PCA one, and the style mixing. So that we choose 12 attributes from the 40 facial attributes, and then we do the classification. We do the classification trainings. Yes, with the sample size. So here the sample size means that we use one single data set images, or we can say the real images, to generate 31 gun views or 31 fake images, which it is very similar to these real images. We combine it together as a bench, so we can say we have the sample size of 32. So in this figure, we showed about the accuracy of the classification of the face attribute Okay, so we can see that in the validation task, in the validation set, they all did very well. They did very well. All of these 3 methods can bring the improvement of the accuracies. However, in the test set, so only the style mix fine means the style mixing operations on 5 layers, So that we can observe that in the test set, only the style mix 5 operations can effectively.
Can you first,
Of course.
Can you explain what this chart is? How is the difference measured? Difference between what?
The difference between the perturbations measures. So suppose we have three methods. the Gaussian one, we sample from the Gaussian distribution, and then the PCA one, and then the style mixing one. We want to compare these three methods.
Okay, so compare these. So you have isotropic, PCA, and style mix, right?
Okay, yes.
How are they? And then you're showing the difference. So difference between what? Between isotropic and what?
Oh, sorry? Isotropic and the PCA and the style mix.
No, but the scale
Okay.
here, you're saying this is, it's a difference. So how do you make, what difference?
Yes, the difference, it means that we don't use any kind of the generator samples. We only use one single images to train our networks. We want to compare with the baseline. So
so what is a baseline? How is the baseline done?
The baseline here, we only use a single dataset images to train the classifier. So we can get our accuracies.
Okay, so what you're saying is then, all right, so this is with and without data augmentation. Is that what you're saying?
Yes.
Okay, so without data augmentation, so what's the data set size difference between your data set and the augmented data? How much bigger is the augmented data?
Oh, sorry, I didn't understand what you say.
So your method basically is increasing the data, right? Using GAN.
Yes.
So baseline doesn't have any GAN generated data. That's what you're saying, right? And that's how they do it, right? Baseline doesn't have any, it only uses real data.
Yes.
So for augmented data or the synthetic data,
okay,
how much was it added in comparison to the real data?
Oh, okay. Here we have our example size here. So in each for each data set images, we generate 31.
Oh, I see. I'm
Okay.
sorry. I didn't read this. So it's 32 times greater. Okay. I'm sorry.
Okay.
I should have read this more carefully. But it's confusing when you say 31 GAN views. So that was a little bit, and it would have been better if you said augmented data size or something like that, because that's the whole idea.
Actually, I don't agree with what you say. So in the classification task, so that we do the decision. We consider about the input real images, the dataset image, and also we need to consider about the decision of the gun views, about the generated samples. So this is not simply add the synthetic images into the dataset. We do it more in the.
Yes, I know.
Yeah.
You are training it with the synthetic data.
Yes.
And that's what they do anyway. For
Okay.
augmented data, you add the augmented data in the training, but the way you did it here is that you came up with this ensemble method of training them. All right.
Okay. Yes.
But that's fine and good. That's not a big deal. What I'm saying is that on the next slide, it's not a big deal, but it just makes it easier if you said ensemble size.
Oh, okay. I understand.
When you say size, I wasn't sure whether you're talking about different attributes or what.
Okay.
So, okay, I got confused there.
Okay.
All I'm saying is that,
okay.
At least for me, if somebody said original data or the true data is one versus, ensemble or the generated data is 31 images generated from one data. So the ratio between baseline data set versus augmented data set is 32 times larger or something like that. That would have made it easier for me. Okay. Fine. Thank you.
Okay. In this figure, it just want to tell us the most effective one, the most effective method. It is the style mix 5 methods. So that we mainly focus on this these methods in the rest of the evaluations. Okay, second one, we want to compare our proposed method to the traditional image augmentation methods. So here we have the color jitter, and the crop jitter, and we have our proposed method, style mix jitter 5. It means 5, not cos. Okay, style mix jitter and the combined one. Combined one means that we combine these 3 jitters together, 3 jitters together, we get our combined jitter. So it shows that if we only use the style mix jitter, it is not better than the traditional one. But if we combine them together, so that we can get an improvement. Okay, we can get an improvement of the classification accuracy. Okay, this is the comparing to the traditional image augmentation methods. Okay, and then how about the sample size? Influence the accuracy of the classification. So it do some kind of the ablation studies of the gun samples. The gun samples means N here, the N here, the N here. If we increase the N here, the numbers of the gun sample here, we can get an improvement of the accuracies. So that basically in the rest of the experiments, the N here it is 31 gun views, 31 generated samples plus 1 real images. So this is what does this figure want to say. Okay. Another data set. We have
so given, if you go back, what
course.
can you say about this performance dip in the low number of GAN samples?
Oh. Okay. Sorry.
What's your thought? I just want to know what you're thinking. Why that
what do I think? Okay, I should read carefully of this paper, but I didn't. So I reckon this decreasing of the performance, maybe it is brought by the something like the by the generated samples. The generated samples number, it is not enough. It cannot bring the enough diversities to the data set. So it decreased. The accuracies decreased due to the diversity of the training samples.
Yeah, but then baseline has less diversity to begin with, right? At least in this one, up to 4 GAN sample, it has 4 times more diversity, right? Versus the baseline.
That's a tricky question. Okay.
I just want to know what your thoughts are. That's all. I don't have an answer myself, but
okay, I will think about it later. Okay, good question.
Right, thanks.
Thank you for your advice. Okay. Okay, about the data set, another data set, car data set. Okay, car data sets. We don't focus on the binary classification task. We have the 3 categories in the car data set, and the cat data set. We have 12 cat breeds. Okay, this is the results here. This is the results of the classification performance on the car data set and the cat data set. So in here, we have 3 kinds of the methods to build our training distributions. The first one, original images. Second one, it is the gun reconstruction. Remember the gun reconstructions here. What's the difference between the style mix 5 augmentation and the gun reconstructions here? Okay, let's go back to the figure here. Gun reconstruction here. That means we don't add so much difference into the reconstruction results. So they're very similar to the original images. But for the style mix file augmentations, we do some slight change on the something like the color of the hair and the color of the car and the color of the eyes of the cat. So we do some slight change. So this is the difference between the gun reconstruction and the style mix file augmentations. So, okay, we just want to make sure that. So the difference between this kind of two methods, we use these two methods to build our training dataset. And then we evaluate on the six methods. Then we do the testing. We do the testing process. Okay, we find that this is really there is a really interesting results here. We find that even the gun reconstruction, it is more stable. It is more stable than the style mix file augmentations. So that this is, I don't know why. So if you add some slightly change on the image, it cannot bring the improvement on the accuracy comparing to the gun reconstruction methods. This is a very interesting result here. I should go back to the paper and find out why it is, but I don't actually have enough time, so I may do it later. So this is the results of the classification accuracies on the car and the cat. Okay, this is the experiments. Okay, conclusions. Okay, finally, conclusion. Oh, not the final one. Okay, the conclusions. So the conclusions in these papers, the authors investigate the capabilities of the style gun to generate alternative views of an input images and use it to the downstream task of the image classification. And then, so it brings three different kind of the perturbations measures for the style gun on the lantern space, which is the isotropic Gaussian noise and the principal component directions and the style mixing. Okay, so also the experiment tells it is the proposed method, it is effective, it can bring the improvement to the classification task of three kind of the three different data sets. Okay, this is this paper I want to present today. Okay, finally, I want to introduce some personal study on the gun inversion. Okay, recently I did some personal research on the gun inversion. Okay, basically it is called the controllable skeleton generations with gun inversion. Okay, I focus on to do the COVID-19 detections based on the post estimation. So you know that the problem is that I cannot find enough data for the skeleton data of the COVID-19 symptoms. So I need to generate it then. So I just do some gun inversion research and to bring an algorithms that I can generate the skeletons of the COVID-19 symptoms, which it is controllable. I can control about the categories of the actions. Okay, here it is some demonstrations. I use the gun inversion to generate the cough action, cough action of the skeleton, which it is one of the very common COVID-19 symptoms. Okay, and the second one, it is to blow the nose, which it is also another kind of the COVID-19 very common symptoms. So this is what I have done. What I have done recently. It is to make a controllable skeleton generation algorithms with the gun inversion. Okay, thank you very much today.
Okay, very good. So on the gun inversion, so this is just the result of the jittering process, right? Using gun inversion, right?
Yes, you're right.
That you were able to synthesize the skeleton, some other versions of the skeleton versions. Okay.
Yes, yes.
Great. Okay, that's super. Thank you.
Okay, thank you very much.
And so in here, that you are trying to generate these sequential frames.
Yes.
Okay, and so what was the methodology you used? Was it that the output is really the entire sequence? Is it input is sequence to sequence model, or how was it done in generator?
It is not simply a sequence model. It is quite complicated. I want to leave it to my next Yongu seminar, maybe. Yeah. Okay. It is basically it is also a gun inversion models, but so it is sequentially generate the joint and the frames of the whole actions. Okay. It is quite complicated. It is not today's content. I just want to show you some possibilities of the gun inversion applications here.
I mean, I agree that you have to think about something like this when you have a very little data, right? And that's when you want to use something like GAN for synthetic data generation. So I'm quite excited that you're looking into this. And I look forward to hearing a little more about what you're really doing in detail, because these figures don't really tell me much about what you're doing.
Yes, I don't really have much time to make the whole PPT materials to tell tell a whole story.
I'll be patient until you give a
okay, thank you very much today.
Well, I really enjoyed it. Great job. Thank you very much.
Okay. Okay, any questions? Okay, I suppose we don't have any questions anymore. So, okay, this is today's presentation. Okay, thank you very much. Thank you, everyone.
Thank you.
Thank you.